Nature's systems can exist in various states and transition between them over time. These states are defined by the system's fundamental parameters. For example, consider a pendulum system. The state of the pendulum can be expressed through angular momentum and position. These two parameters suffice to describe all possible states of the system. Phase space is a multidimensional space encompassing all possible states of a system based on its fundamental parameters, capturing the system's evolution over time. At any given moment, a point in phase space represents the system's state. This state evolves over time, and the system's trajectory in phase space can be traced to analyze its life and evolution. Angular momentum and position are vector quantities and thus can take different values along 3 spatial dimensions. Consequently, each of these parameters has 3 degrees of freedom. For a pendulum system, this implies that its phase space is 6-dimensional. In general, the dimensionality of a system's phase space equals the total degrees of freedom of the system. Each dimension in phase space represents a variable of the system, for example, position and momentum. A point in this space represents the system's instantaneous state, while its evolution over time forms a trajectory. Phase space is a powerful tool for understanding the behavior of complex systems, allowing scientists to analyze a system's motion and potential behaviors just by examining its representation in phase space. However, for complex classical systems and fields like quantum mechanics or statistical physics, phase space may not always be practical or intuitive. In these cases, phase space dimensions often exceed 3 or may even be infinite, making visualization challenging or impossible. The Hamiltonian is represented as a dimension in phase space, facilitating the analysis of a system's time evolution via other parameters. In classical physics, using Hamiltonian and Lagrangian mechanics simplifies the mathematical treatment of complex systems, achieving what Newtonian mechanics hard to do. The Hamiltonian phase space approach also applies to quantum and statistical physics, enabling the study of system evolution and visualizing equations like Schrödinger's equation and density matrices. In quantum mechanics, phase space incorporates probabilities and states, with the wave function represented as a vector. Schrödinger's equation describes how this vector's orientation changes over time. In statistical physics, phase space visualizes the distribution of particle states and the number of particles in each state, revealing a system's quantum properties and general characteristics shaped by thermodynamic laws. In nature, systems can converge to certain states over time or exhibit periodic or aperiodic motion around them. These behaviors are observable in phase space. If an object approaches a state or moves periodically, non-periodically around it, the state is called an attractor. Attractors often correspond to the state of lowest energy for the system. However, attractor states do not always represent minimum energy, as energy barriers may prevent the system from reaching lower energy states, leading to stable and unstable equilibrium states. Stable equilibrium states are fundamental attractors. If energy is added to the system, it eventually loses energy and returns to the stable state. Unstable attractors toss equilibrium states, however, can be disrupted by minor disturbances, making it unlikely for the system to return to the attractor once perturbed. For general relativity, a black hole's curved spacetime creates an energy gradient, and the position of a planet in this spacetime determines its energy level. By plotting position and energy in phase space, one can observe the planet being drawn toward the black hole. For classical mechanics, consider a periodic oscillation of a spring. If potential energy and the mass's x position define the phase space, a frictionless spring shows periodic motion around an attractor. With friction, the system evolves toward a stable equilibrium attractor. For statistical physics, define phase space with parameters like momentum and thermal energy for many particles. The system evolves toward an attractor corresponding to minimum total energy, shaped by thermodynamic laws. For quantum mechanics, in an atom, electron energy levels form attractors in phase space, defined by potential energy and distance. Electrons in excited states are drawn toward lower energy quantum attractors. If a system experiences an energy-reducing effect, it approaches these attractors over time. However, if the system neither loses energy nor undergoes energy conversion, different types of attractors emerge. If a system can lose energy, it is drawn toward a nearby attractor, and over time, the system evolves into the state defined by that attractor. These attractors are called fixed-point attractors. The most well-known example is a pendulum oscillating in an environment with friction. The pendulum may initially possess high potential energy, but over time, it loses energy due to friction and settles at a stationary point. This stationary point represents the fixed-point attractor in the system's phase space. Some systems can form a specific loop in phase space by either not losing energy or maintaining a constant energy level. In such systems, attractors are closed loops or rings in the phase space. These are called limit cycle attractors. Examples include the periodic motion in a clock mechanism or a pendulum oscillating without friction, which are examples of periodic attractors. Torus attractors represent regular and periodic behaviors, and they are typically found in deterministic and orderly systems. In phase space, the trajectories revolve on a torus, a donut-shaped surface. These trajectories often exhibit quasi-periodic behavior, meaning the system has multiple periods that are incommensurate with each other. For example, consider an oscillating system with two different frequencies. The system exhibits quasi-periodic motion encompassing both frequencies. This behavior corresponds to a toroidal structure in phase space. In complex systems, especially those with chaotic dynamics, the system may trace seemingly random trajectories in phase space that actually exhibit a hidden order. Strange attractors, unlike regular torus attractors, present a structure that appears both deterministic and random. These attractors often display fractal geometries, indicating extreme sensitivity to initial conditions, which makes long-term predictions challenging. The Lorentz system is one of the most famous examples of chaotic attractors. Chaotic attractors can also be observed in atmospheric motion or fluid dynamics. Additionally, a system with toroidal trajectories may initially exhibit quasi-periodic motion. However, when the system's parameters change, e.g., through a bifurcation, the toroidal structure may break down, giving rise to a chaotic, strange attractor. The complexity of nature can be better understood by examining the behaviors of different systems over time. Phase space offers a powerful tool for visualizing and analyzing these behaviors. Classical physics, statistical physics, and quantum mechanics each allow us to understand how systems evolve within phase space on different scales. Attractors are the fundamental building blocks that determine the long-term behavior of a system and reflect the order or chaos of nature. In this context, phase space and attractors not only provide a mathematical representation of physical systems, but also serve as a visual guide to understanding the underlying principles of order, chaos, and evolution in nature. In conclusion, for anyone seeking to understand the workings of nature, phase space is the map of the journey between order and chaos. Attractors act as the signposts on this journey, showing where systems evolve in the long run. Exploring the simplicity and complexity of nature through phase space and attractors whispers a profound truth. Within chaos lies order, and among randomness, there is purpose.